So we have Benjamin Peters here from Viasat that's going to give this talk, TCP HyStart performance over satellite links. Let's give him a round of applause. Thank you, everybody. All right, and with that, we're going to start playing this video. We're about 5 minutes late, so thank you. All right, let's get started. Okay, and Benjamin and I are going to go backstage till next.
Good afternoon. My name is Ben Peters. I am an undergraduate at Worcester Polytechnic Institute. And this spring and summer, I've been working with my fellow undergrad, Pinhan Zhao, under the advisement of Professor Mark Claypool and Jae Chung from Viasat. And we've been looking at TCP performance over satellite networks, especially looking at the impact of HyStart on startup performance. So we're looking at satellites, and the reason we're looking at satellites is because they cover everywhere, and they provide global networking. Satellites are accessible for situations where traditional wired networking isn't available, such as remote locations, on airplanes, and during emergencies. And recent developments in satellite technology has increased the available bandwidth by over 20% in the last few years. However, due to the physics involved, one-way trip times remain at about 300 milliseconds, meaning a minimum round trip time is about 600 milliseconds. This makes modern satellite networks both high bandwidth and high delay networks, as opposed to the low bandwidth, high delay networks that they had been in the past. When we were looking at performance, we noticed two causes of performance degradation. The first cause we discovered was that the sender and receiver buffer sizes were too small, and that didn't allow for full link utilization. The second issue that we discovered was that HyStart, which is designed to exit slow start early in order to avoid overshooting the link, actually exited slow start prematurely in our situation and hurt performance. We're especially interested in satellite performance because performance-enhancing proxies and TCP proxies that have long been the saving grace of these connections are becoming increasingly ineffective as VPNs and encrypted protocols like QUIC take hold. We've also been looking at satellites because there are few published studies on actual satellite networks, and most of the studies that do exist are just using simulation or emulation. So just a quick roadmap. We just finished up our introduction and some background. Next up, I will talk about the testbed and our methodology before diving into some results from buffer settings and our HyStart experiments. Our testbed was set up with a client that was connected to the Viasat network in order to represent a user with a last mile satellite connection. We also set up servers at WPI that were connected through the internet to our client. We ran 5 to 10 experiments serially interlaced in order to minimize the impact of temporal differences in the network. Our Viasat plan allows for about 144 megabits per second of download with a 600 millisecond round trip time. And that makes the BDP about 10.8 megabytes. All machines in our testbed were running Linux kernel version 4.15.0, and the performance-enhancing proxy that Viasat deploys by default was disabled for all trials. Taking some initial looks at performance, we can see on the right I have a graph of throughput versus time. The orange line represents the average of 5 runs. Orange means that auto-tune was enabled. Auto-tune is receiver buffer auto-tuning, and that dynamically adjusts the receiver buffer size in order to allow for full use up to the maximum allowed size. The blue line, which you can hardly see in this graph, represents runs without auto-tune, and the shaded region around them represents a 95% confidence interval. We also collected other statistics, such as the round-trip time, the advertised receiver window in megabytes, the advertised congestion window in megabytes, and the retransmission rate. So this was a initial trial with all of the Linux default settings, and so that means HyStart is enabled, and by default AutoTune is enabled, but we are testing with and without AutoTune to evaluate some claims about its startup performance impact. We also have left the receiver memory and sender memory, or WMM, at their default values. The first number indicates the minimum amount available to each socket. The second number is the starting size of the buffer, and the third number is the maximum size. And TCP only advertises up to half of this size, with the other half being reserved for overhead. Taking a look at what we actually saw for performance, we found that the throughput was significantly limited in cases with AutoTune by the sender buffer size, and that was capped at about 4 megabits. And we found that that was far below our BDP, and that caused performance that was far below our expected link utilization. For runs without AutoTune, we saw even worse performance, and that's because it was not able to increase its receiver buffer size from the 128 kilobytes that it started with. So overall, we see that utilization is far below the link capacity, and it's significantly worse without AutoTune. As a first step, we increase the receiver memory, and we increase that to 60 megabytes for all values. So that means it starts with 60 megabytes, and it can only grow up to 60 megabytes. And we chose 60 megabytes because it's a somewhat arbitrary number that is larger than our bandwidth delay product, meaning that we should be able to get full link utilization. What we can see is that runs both with and without AutoTune perform very, very similarly to each other, and that they are both capped at about the same place as the prior runs with AutoTune. And again, that's because the sender buffer size is growing to as large as 4 megabytes, which simply is not large enough to feed our link. We do notice, interestingly, that the receiver window that's advertised does grow more slowly with AutoTune enabled, and that's because it dynamically allocates that based on throughput. And so with low throughput, it doesn't increase the window very large until it needs to. So we don't see any performance impact because of this receiver window size. The takeaways from this is that increasing the receiver buffer means some improvement without AutoTune, but no improvement with AutoTune, and that we are still well below our expected throughput on our link. And importantly, we do learn that when we set the default or starting size and the maximum size of the receiver memory to be the same, that runs with and without AutoTune perform very similarly to each other. As a next step, we increase the sender buffer size, and so we put the receiver buffer size back down to its defaults, and we increase the sender buffer size up to 60 megabytes for all values. And then we looked at performance again. From here, we can see that runs with AutoTune are actually do have a slightly increased performance. And that's just because we've gone from a 4 megabit cap to a 6 megabyte cap being held back by the maximum size of the receiver memory at this point. As we would expect, runs without AutoTune are again capped at the 128 kilobytes, and so they get almost no performance on this link. So increasing the sender buffer does improve performance for AutoTune streams, and that's just because the larger maximum value of the receiver memory than the sender memory. However, we still find that we're only using about half of our link throughput, not even hitting 50 megabytes per second, which is far below what we would expect for our throughput. So taking it all and putting it together, we increased all of our buffers up to 60 megabytes, and we found full link utilization, and we found that the performance between runs with and without AutoTune was pretty much the same. So again, we learned increasing the buffers results in full link utilization, and we found that runs are visually very similar with and without auto-tune. And that's just because the buffer sizes are now larger than the BDP. So to evaluate some claims from previous work that indicates that startup performance is impacted by the auto-tune feature, we are just looking at the first 15 seconds of the previous chart, and that just gives us a better view of throughput. Taking a look at the throughput, we see that there's almost no difference between them, and that the averages for the other are completely contained within the confidence interval of the other runs. So with and without autotune appear to grow exponentially, and autotune does not appear to be inhibiting the growth of the throughput. And if we take a look at the growth of the receiver window, we see that it's even closer than the growth of the throughput, indicating that variations in the throughput are caused by other symptoms or other factors, and not by the receiver window size. What's the takeaway? That means that there's really no difference between runs with and without autotune, indicating that autotune is not impacting the performance of slow start. So what are some recommendations we have about autotune? So as it is right now, autotune should remain enabled by default. And that is because we found that it increased the buffer size up to the maximum so that the throughputs on these high BDP links could be reached without requiring that much memory allocated all the time. We also found that it didn't impact startup performance, so there should be no reason to disable it. Looking at tuning those actual buffer values, we recommend increasing the maximum value that the buffer can be to about 25 megabytes. And we chose that number because, again, TCP only advertises half of that. And so that would allow for links with up to a 12.5 megabyte BDP to make full utilization of this, of the link. So just a quick update on where we're at. We just finished up our buffer settings. Next up, we'll look at HyStart results, and then we'll wrap things up. So just an initial look at runs where HyStart is enabled or disabled. These are all runs with the default settings on Linux. So that means autotune is enabled, but we did increase the receiver memory and the sender memory up to 60 megabytes in order to get the full utilization of our link. These were also 1 gigabyte downloads, and they were run serially interlaced. Taking a look at startup, we find that HyStart off increases its throughput much faster than HyStart on, and it reaches its steady state much earlier. As a result, we also find that it finishes the download earlier than runs with HyStart on. In fact, it actually reaches its steady state about 20 seconds prior to HyStart on, and as a result, it again finishes 25 seconds earlier than runs with HyStart on. So from that last graph, we computed download times of different sized objects. So in this graph, download size is on the x-axis and the time is on the y-axis. So higher is actually worse in this case. So we can see that for the smallest objects we computed, which were 1 megabyte downloads, they take about 50% longer with HyStart enabled compared to HyStart disabled. And for the average website, which is about 5 megabytes these days, it takes twice as long for runs with HyStart on to download that much data. So this has a very significant impact on user performance or user experience because websites and small data downloads especially take longer with HyStart on because it affects the slow start performance so much. So we wanted to take a closer look at why HyStart is exiting. And so HyStart actually looks for one of two signals in order to exit slow start. The first signal it looks for are packet trains. And so it uses these packet trains to estimate the bandwidth of the bottleneck link. And then it exits slow start when it approaches that bottleneck link. or that bottleneck throughput. The second thing it looks for is the increase in round trip delay time. And so this monitors round trip times, and if they increase over a threshold, it exits slow start and moves to congestion avoidance. Normally, this is a wanted behavior as it causes slow start to exit before loss is achieved, which often leads to high loss and low throughput for a short period. But in our case, it was exiting too early, and it was actually degrading performance. So you can actually enable or disable each of these signals on its own. And so we ran a series of runs with only the packet train signal enabled. And then we ran a series with only the delay signal enabled. And then we compared that to runs with both enabled, and then runs with HyStart off. Looking at the performance of the packet train only and HyStart off flows, we found that they were very similar to each other. And that would indicate that the packet train signal is not causing HyStart to exit early. And if it is causing HyStart to exit, it is exiting at an appropriate time. Additionally, we found that runs with only the delay signal enabled, they performed very similarly to runs with both the delay and the packet train signal, indicating that the delay signal is really what's causing HyStart to exit early. Looking more closely at the round trip times for our data, we plotted these graphs on the right. The right one, or the upper one, is the round trip time in seconds, with the lower one being the round trip time difference in milliseconds. And the red vertical line represents when HyStart exited slow start. So looking at our data, we found that HyStart exited only 15 to 22 acts into the stream, which was far before the full link utilization was reached. And so that was because the HyStart max delay, which is the upper bound for the HyStart delay threshold, is fixed at only 16 milliseconds in the Linux kernel, which in our case is only about 3% of our total round trip time, which is a very small amount of deviation. So we found that delay changes regularly exceeded that 16 milliseconds. As you can see in the bottom graph, there are lots of values that are higher than 16 milliseconds. And so that caused HyStart to exit early, thinking that it was reaching congestion, when really it was just a variable, a high variation in round trip time, but a very low percentage variation in our round trip. So our recommendations is that HyStart delay max should actually be variable based on network conditions instead of a constant value. Tracking the average and the standard deviation statistics should be sufficient for keeping track of this round trip time and determining an appropriate threshold. But more testing is needed to determine an appropriate value and how exactly that should exit. Down here at the bottom, we do have a sample bit of code that only uses a exponential weighted average, and it just takes a percentage of that average and sets that as the threshold. This would allow for higher delay links to have a higher threshold, as opposed and be treated hopefully more fairly in terms of HyStart's performance when compared to these smaller links. So in conclusion, satellites are everywhere, and these performance-enhancing proxies and TCP proxies are becoming increasingly ineffective, meaning that it's more important than ever that we improve the overall performance over satellites without these. We found that increasing the default buffer sizes on Linux actually led to better performance over high BDP networks, and so this transcends just satellite networks to any high BDP network, and increasing these would help any of those networks. We also found that buffer auto-tuning is effective, and it does not limit the exponential growth during slow start, and so it should remain enabled by default on Linux because it doesn't impact performance. Lastly, we looked at HyStart and how it exits slow start prematurely, and we found that it was due to high variation in round trip times, and that's especially common on wireless links or high delay links in general. Looking to the future, we are looking to look more into this HyStart RTT-based exit, finding the appropriate values and an implementation that works, and testing it on various different network conditions, as well as our satellite connection. We're also interested in looking at the HyStart++ protocol that's been proposed and implemented in Windows to see if that helps solve some of the issues that we found with HyStart, and whether or not that improves performance. Additionally, we're interested in other TCP settings over satellite networks, including the initial congestion window, fast conversions, the beta parameter, and the HyStart RTT0 variable. Lastly, we're also looking at competing flows over the satellite links. We are looking at protocols like BBR, HyBLA, and QUIC, all competing for bandwidth over these high delay links. Thank you very much for your attention, and we will now take any questions or comments.
All right, thank you, everybody. Now we're going to bring in Benjamin on the stage. All right, stop it. Benjamin, that's just applause for you, man. Okay, so there's a couple of questions. Number one is from Michael Richardson. So I'm going to put that on the stage. Michael, if you want to come on and speak, just raise your hand and I'll see you and then I'll bring you in. Okay. So here's the first question. And I'm going to also bring in Michael here as well. All right. Go ahead, Michael.
So I'm interested in buffer bloat over satellite link, and I'm wondering whether when you did your work, whether you could tell whether the satellite link was in fact buffering more of your data than it should have, causing queues to run up. And so I'm wondering if you did any kind of, if your data was able to determine, I guess you had some round trip analysis, and whether or not you could see whether the buffers were filling, and whether or not you did any parallel tests with other flows to see if there was in fact a bloat that you were exploiting to get better bandwidth.
Yeah, so we did monitor the round trip time. Did the increased round trip times at steady state, indicating that the buffers were being filled. One of the things Cubic is well known for is its buffer fill property. And I believe at Viasat they have 18 megabyte buffer with beyond, or I believe it's 36 megabytes, and then at 18 megabytes it starts dropping every fourth packet. So I believe we did see that buffer was filled, but I don't believe that was that filling. I believe that we were really limited by the Linux kernel buffer sizes as opposed to having to fill that buffer.
So you saw your window close, is what you're saying at that point. If you're limited by receive buffering, then you wouldn't have received enough ACK to continue sending.
Right. That's what we saw. We saw very small advertised buffers, and we talked about our BDP was 10.8 megabytes. So anytime the Linux sender or receiver kernel buffer sizes were smaller than that, we couldn't get full throughput. We didn't have one BDP worth of packets.
And I guess the obvious question is, did you try this over SpaceX, over Starlink?
We did not try it over a lower bandwidth or a lower latency. So.
Great if you had a chance to do that. There are some people that have equipment that where you can access both ends of it. Dave Pat and the Buffer Bloat crew have a lot of stuff set up. So if you want to try it again, do it remotely. You don't even have to get one.
Yeah, that would be awesome, because that offers lower round time, which is what we think is the largest hurdle.
Cool. Thank you.
Benjamin, I think there's a lot of feedback or echo coming from your side, like a very high frequency sound. Can you mute for a sec?
Yeah.
Okay, that was you. Okay, so I'm gonna have you keep it that way until you're trying to speak, if you don't mind. So the next question is from Neil. I'm gonna show it on the stage. Neil, if you want to come up on stage, just raise your hand in the raised hand section, and I'll bring you up. That's the question from Neil Caldwell. Benjamin, if you can respond.
Yeah, I think that's definitely something that we can consider. I'm not entirely confident why it was implemented in the first place. I think that possibly just removing it overall might be the best solution. Because if the kernel does dynamically adjust the threshold, but it does not adjust the maximum, that could be.
If you don't mind, keep muting Benjamin.
Yeah, sorry.
Okay, we lost Neil. Neil, if you want back, just raise your hand and I'll bring you back in. Okay, I am probably going to read the second one. Okay, I'll put the second question here. Okay, you see that, Benjamin?
Yeah, so we've actually been looking at trying to implement in a kernel and test that on our network. We're also working on setting up an emulation system so that other network conditions, including the lower latency links. We want to make sure that decreasing performance on those more common.
Okay, and there's a commentary from Eric Dumazet, which I'm just going to show here. That we probably need to double check the original HyStart paper for rationale of the 60 millisecond value. That, you mentioned that in your talk, I think. Okay, next question is, I guess, yeah, that was, did I miss anybody? I'm going to mark everybody's answered. Okay. Any more questions? Anybody raise your hand or type on the QA tab, please. Okay, so if there are no more questions, let's give a hand of applause for Benjamin. The excellent talk. Okay, thanks, Benjamin. Okay, we'll go on a break now for about until the next session. Feel free to use the tables. We have a lot of tables available. You can join the tables, chit chat, give us some feedback on that experience. And with that, I'm gonna end the session.